Okay, welcome back. We're going to continue 6a. We've been talking about inner product spaces. I think maybe the last thing that I said on Friday is that inner products know about lengths. Right? We discussed how they know about lengths. Right? The point was that in Rn, the length of V, I mean, you're used to thinking about lengths in Rn, it was just the square root of V dot V. Gives you the same thing, which in our new inner product language is the square root of the inner product of the vector V with itself. And this thing was the thing we called the norm of V in any inner product space. Right, so the middle part with the dot product, that's an Rn, but if you ignore the dot product in the middle, this applies in any inner product space. Okay, but also, inner products also know about angles in your space. Right, because in Rn, maybe you remember this from calculus, two vectors u and v are perpendicular if u dot v equals 0. Maybe you remember this from calculus, which in our new inner product language should be if the inner product of these two vectors is 0. Okay, so what we'll do is we'll generalize this notion. We'll just say that in an inner product space, if two vectors have an inner product of 0, well, we'll use a different word. We'll call those two vectors orthogonal. So two vectors u, v, and v, where v is an inner product space, are called orthogonal if their inner product is 0. Okay, so this concept is defined in any inner product space, right? And we saw at least one example of an interesting inner product space where you take two functions, you multiply them, and you integrate from -1 to 1. That gives you an inner product. It's sort of hard to think about geometry in that space. But if you take the definition to be, okay, well, you're orthogonal if your inner product of the two vectors is 0, then whatever we prove about orthogonality should hold for that inner product space. Of course, in our heads, the picture that we draw, the picture that we think about in our heads are perpendicular vectors in Rn. That's the prototypical example. Just a remark that if uv equals 0, the inner product of v and v, then also the inner product of v and u, this is supposed to be the complex conjugate of the inner product of u and v, but of course the complex conjugate of 0 is just 0. Right, so in other words, in this definition of orthogonal, it kind of seemed like the order of the vectors matters. Right, in other words, it seems like maybe u could be orthogonal to v, but v might not be orthogonal to u if you switch the roles of u and v. But if the inner product of u and v is 0, then the inner product of v and u is 0, which is why it makes sense to just talk about two vectors being orthogonal. The order that you take their inner product in doesn't matter because the inner product equals 0. Okay, so this definition is symmetric in u and v. That's what I'm trying to say. So let's prove our first sort of baby results about orthogonal vectors. So one is that 0 is orthogonal to every vector in V. The 0 vector is orthogonal to everything. Also, 0 is the only vector which is orthogonal to itself. Okay, and both of these results are actually almost one-liners. In particular, one, we actually already proved one last time. I'll include a reference in the notes, of course. But one, we proved that for every vector u and v, the inner product of 0 and u equals 0. So this is just restating that result. 0 is orthogonal to everything. 2, I need to prove that 0 is the only vector that's orthogonal to itself. So if v is orthogonal to itself, I don't know why I switched from u to v. Then, by definition, this means that the inner product of v and v is 0. But by the axioms of an inner product, can I find it? By the axioms of an inner product, by definiteness, the inner product of v with itself is 0 if and only if v is the 0 vector. So this is actually just a restatement of definiteness, the definiteness axiom. This implies that v is 0. Therefore, 0 is the only vector that's orthogonal to itself. And again, if we think in terms of vectors in Rn and perpendicularness, it's sort of clear that no vector points at a right angle to itself, right? Except, of course, right, when you think about the 0 vector, it's a little bit weird. The 0 vector doesn't really make any angles with any other vector, but the dot product of 0 with any vector is definitely 0. And since that's what we mean by orthogonal, 0 will be orthogonal to every vector, including itself. Okay. The next result is maybe the most famous theorem. If you ask like a random stranger on the street to name a theorem from mathematics, I bet the plurality of them would say the Pythagorean theorem. Okay, and I'll talk after I write down the theorem about why this is called the Pythagorean theorem. It's a bit more general. So suppose that u and v are orthogonal. Then the norm of u plus v squared equals the norm of u squared plus the norm of v squared. Okay, so the point is that if you write down, let's say you draw a picture of what this means in R2, what it means is exactly the classical statement of the Pythagorean theorem. However, it will hold in any inner product space, right? In any inner product space, you can define the norm of a vector. Once you have the norm of a vector, you can talk about this equation, whether it's true or not. In any vector space, in any inner product space, you can talk about orthogonality of vectors. So our intuition is guided by Rn, but our proof should work for any inner product space. But what's the picture? Okay, so here we're in R2. Suppose that you have a vector u, looks like this. I'm assuming that u and v are orthogonal, which in R2 means that they're perpendicular. I should try to draw them. So these are orthogonal vectors. What is u plus v? Well, if you complete the parallelogram, which in this case is a rectangle, it doesn't really look like one, but it's supposed to be. This vector is u plus v. All right, but since this parallelogram that I've drawn is supposed to be a rectangle, it means that two diagonals have the same length. So that diagonal has the same length as this diagonal. So what this result is saying is that the length of the red thing squared plus the length of the blue thing squared equals the length of the green thing squared, which is the classical Pythagorean theorem. Okay, so Pythagoras, the result attributed to Pythagoras is when v equals R2 with the dot product. Okay, but actually the proof, once you've developed all this technology of inner product spaces, is just an easy computation. Okay, so just a computation. What am I interested in? I'm interested in the norm of u plus v quantity squared. Anytime you see a norm squared, you should think, oh, that's just the inner product of the vector with itself. The norm of u plus v squared is just u plus v inner product with u plus v. And now inner products are additive in both coordinates, right? So let's do this in excruciating detail. I can use additivity in the first coordinate, the first slot. And then on each of these, I can use additivity in the second slot. Okay, so this one is just by additivity in both slots. And now u and v are supposed to be orthogonal. So this is 0, this is 0. And what you're left with, the inner product of u with itself, that's the norm of u squared plus the norm of v squared. Okay, so this proof works totally in general. So now you have a Pythagorean theorem in every single inner product space. And again, I've probably said this already too many times, I'll continue to say it. When you're working in inner product spaces, all of your intuition should be guided by the geometric things that you know about Rn, and then your proofs should work in general. As an example, we have we'll see that this is a very useful result, but I'll draw a picture. So let u and v be vectors in V with V non-zero. Then, so I just have any two vectors except that one is non-zero. There exists a scalar C and F such that W, which is u minus CV, is orthogonal to V. In particular, C equals the inner product of u and v over the norm of v squared. Okay, so lots to unpack here. The thing to do, though, is to draw the picture in R2. That is how we're going to understand this. Okay, so here's the picture. Maybe I'll draw it off to the side. So the picture is, we have like a vector u here. We have like a vector, let me just make it a bit shorter, v here. What this is saying, all right, let me mark up what we're getting, is that you can find a vector w that's orthogonal to v, right? Maybe I'll underline it in green because that's what I'll draw w in eventually. So that means a vector that's like going in this direction, right, in this picture. And another way to say that w is equal to u minus cv is to say that cv plus w equals u. So what is this saying? This is saying that you can go some amount in the v direction. You can scale v to get to cv, and then move orthogonally to v to get to u. It's not the best picture. Here's w. And here I've scaled, so this small vector is v, this long vector is cv. And it seems reasonable that you can do this as long as you start with a non-zero vector, right? As you scale v, you're shrinking or you're stretching v in both directions until you get to a point where you can just make a right angle turn and walk to u in that direction. That's what this is saying, right? I mean, if you were some other vector, right, if you were sitting over here, what you would do is you would just walk this direction in v, you would scale v by some negative scalar, and then you'd walk this direction w to get to u. And no matter where u is in this picture, it seems like it should always be possible to do this. Okay, this result also tells you, though, what the scalar is, right? What the scalar is it's the inner product of u and v over the length of v squared. Another way that you can think about this theorem is you can think of this theorem as you can take u and you can project it onto v. So you just go down at a right angle from u, you project it onto v, that's some scalar multiple of v. If you take that scalar multiple and you add something orthogonal, you get back to u. Okay, so how do you prove this? It should work in the abstract, but that's the picture. What do we want? We want W to be orthogonal to V. So we want the inner product of W with V to be 0. That's what we want. We want to figure out what C will allow us to do this. But inner products are linear in their first slot. That means you can break them up over a subtraction, pull out the scalar. Right, but this, you see a vector inner product with itself, you should think, that's the norm squared. That's the norm squared. And as long as the length of V is not 0, we can solve for C. And note, the length of V is not 0 because we're assuming that V is non-zero. Right, so since the length of V squared is not 0, since V is not 0, that means that C is equal to the inner product of U and V divided by the length of V squared. Right, in particular, there's only one scalar because you can just solve for it. If this vector for any C is going to be orthogonal to V, you can just solve for what the scalar has to be. So this is the unique scalar. Okay, and this seems like kind of a technical result. Right, it seems like, okay, well, why do you care about this? We can use this to prove a really fundamental result, which is important in many, many fields of mathematics. You may have even heard the word before. It's called the Cauchy-Schwarz inequality. Okay, so let me just get on my notes. Cauchy-Schwarz inequality. Okay, what does it say? If U and V are vectors in V, then the absolute value of the inner product of U and V. So remember, the inner product of U and V, that's just some scalar. That's either a real number or a complex number. And we know how to take the absolute value of a real number, the absolute value of a complex number, you take the complex number, multiply by its conjugate, and you take the square root. You could do that for a real number too, but it's the same thing as just taking the absolute value. So this is now a real number, a non-negative real number. This number is less than or equal to the norm of U times the norm of V. These things are also non-negative real numbers. Okay, equality holds if and only if one of U or V is a scalar multiple of the other. Okay, so this says that the length of the inner product of two vectors is controlled by the length of the two vectors themselves. Okay, and we will, it turns out that this is a useful inequality. It might not be that obvious, but there's at least one homework exercise, if I remember to assign it, which I think I will. I don't always, which will show that you can use this inequality to prove kind of non-obvious things. But the proof is actually not so bad. So clearly, if V equals 0, then both sides are 0. Right, the length of v is 0, and then also you take the inner product, you get 0. So in that case, the inequality is true, and also 0 is a scalar multiple of v. Sorry, v is, yeah, also u is a scalar multiple. Sorry, v is a scalar multiple of u. Which is part of the claim, right? Since we have equality here, it must be that one of them is a scalar multiple of the other. Okay, so we're okay if v is 0, so let's suppose that v is non-zero. Now, by the previous result, I have a non-zero vector. It means that I can get a vector that's orthogonal to it by subtracting from u. If I have a non-zero vector v, I can get an orthogonal vector to v. So by the previous result, w equals u minus the inner product of u and v divided by the length of v squared. V is orthogonal to v. So rewriting this, this is going to drive me crazy. So I really don't know why this happens occasionally. Rewriting this means that u is equal to w plus uv over the norm of v squared v. Right, and w is orthogonal to v. So that means that we can use the Pythagorean theorem, right? This and this, these are orthogonal. So by the Pythagorean theorem, the norm of u squared is equal to the norm of w squared plus the norm of this whole vector. V. Okay, but this thing here, this is just a scalar. And I can pull scalars out of an inner product at the cost of taking the absolute value. Right, so this is the norm of w squared plus the absolute, sorry, there should be a squared here, right? So I can pull out this scalar. Okay, so it'll be this whole thing squared, and then I could distribute the squared over the scalar and the norm of this vector. Right, okay. But this is, right, whatever in here is just the length of two scalars divided by each other, and I've taken their absolute value. So this is the same thing as the absolute value of uv inner product squared over the norm of v squared, because this one, if you take the absolute value, I mean, it's a non-negative real number, so you don't need the absolute value. So these things, these norm of v squareds, sorry, there's an extra squared, right? This is kind of a torturous way to write this. There's an extra squared, right? In the end, you get norm of v to the fourth. So one of them cancels. Okay, and the point is that this thing is bigger than or equal to just the left term. Right, everything inside has been equality so far, but now I can just ignore. It's kind of amazing that this inequality is so powerful because it just comes from just ignoring a term that could very well be non-zero. Right, so now you can just clear denominators to conclude what you want. And you also take square roots, I guess. Okay. Man, this is going to probably print annoyingly for you, but probably you aren't printing these anyway, so what am I worried about? So now clear denominators and take square roots. Okay, also, we said that equality will hold if and only if one of u or v is a scalar multiple of the other. So note that equality holds if and only if the length of w squared equals 0. Or that's the only thing that we dropped in this last line, which happens if and only if w is 0. But if w is 0, that just means that u is, right, going up here. If you put w equals 0, it just says that u is a scalar multiple of v. So this will, actually it's if and only if, right? Okay, or alternatively, you think of this picture, right? The only way that you'll get this w to be 0 in this picture is to have u swing all the way down to actually be pointing in the same direction as v. Okay, so the Cauchy-Schwarz inequality, again, let's take another look at it. It turns out it's extremely powerful. It says that the length of an inner product of a vector with itself is bounded above by the product of the norms of the vectors you're inner producting. Okay, and now my other computer is acting up, the one that I hold notes on. It's not a good day for me computer-wise, but I can at least see that the next bit. So as a corollary, we get the triangle inequality. Okay, one of the most useful, truly one of the most useful inequalities. You'll see what I mean when you eventually take an analysis class. Maybe you've already taken 327 actually. So if you've already taken 327, then you know about the triangle inequality, at least for the reals. Holds an inner product space actually. What does the triangle inequality say? It just says, suppose you have two vectors in an inner product space, then the norm of u plus v is less than or equal to the norm of u plus the norm of v. And equality holds if and only if one is a non-negative scalar multiple of the other. Right, in other words, they not only point in the same direction, but they even point in the same direction. They're not one of them isn't actually pointing backwards. What's the picture here? The picture here is, maybe this time I should actually try to draw a triangle. Here's u. I'm gonna move v over here so that it's clear what we're talking about. Here's v. This vector is u plus v. And so I've translated v from the origin, but that's fine. You should be used to adding vectors like this, right? All this is saying is if you move in this direction and then move in this direction, that was a longer path than just going directly from here to here in a straight line. And going via a detour always takes at least as long as going in a straight line. In other words, I mean, the geometric way to state this is if you take any triangle, you add two of the side lengths, it's got to be greater than that other side, because you can draw this exact picture, right? Going along one side and the other, there's a faster way to get there. You can just go directly to the point that you're interested in. That's why it's called the triangle inequality. And this inequality, of course, holds for absolute values in R. And when you take analysis, you use this inequality all the dang time. And the proof is Okay. It's just a computation, but maybe it's a slightly less obvious computation than the ones we've done so far. Okay, so it's the proof, just a computation. Let's consider the norm of u plus v squared. Okay, because anytime you see a norm, you want to talk about an inner product. As we sort of said, sometimes it's easier to work with the square of the norm. This thing is just the inner product of u plus v with itself. Again, let's use linearity. Use linearity a bunch to write this as 4 terms. This is essentially exactly the same as that first proof that we did today. Now, though, this one is the norm of u squared. That's good. This one is the norm of v squared. That's also good. Here, I don't know that u and v are orthogonal. As I've drawn them, they clearly aren't. But we can at least complex conjugate to swap the order in the second one. Now at least they're in the same order. Okay, but what is this? What is this nonsense? If the inner product of u and b is a plus bi, what you'll get is you'll get a plus bi plus a minus bi. Right? That's what happens when you add a complex number to its complex conjugate. What do you get? You just get 2a. So this thing is actually the norm of u squared plus the norm of v squared plus 2 times the real part of the inner product of u and v. Right? Again, if you were working over R, then you would just get 2 times the inner product of u and v. But if you're working over C, you get 2 times the real part. Okay, now this is less than or equal to just 2 times the length, the absolute value of this scalar. Right? What's the picture here? This picture actually is true to life. This is not just, this is a scalar. So we can think of it as living in C. Even if it's a real number, it still lives in C. It just lives along the real axis. Right? So the inner product of u and v is just some scalar sitting out here. Right? This is the inner product of u and v. It's just a scalar. And the length of it is definitely bigger than the length of just the real part. Right? No matter where on the complex plane you put that vector, if you look at the length of the real part, it's always going to be shorter because it's not going up at all. So that justifies that inequality. And this now, I can use Cauchy-Schwarz. This is less than or equal to 2 times the length of u, the norm of u times the norm of v. So this one is the Cauchy-Schwarz inequality that we just proved. And now this whole thing is just the square of u, the norm of u plus the norm of v. So if you take square roots of both sides, then you get the inequality that you want. Okay, so that shows that this inequality holds. What about the equality part of it? Well, this will be an equality if only if these 2 steps are actually equality. Okay, the second step we know is equality if and only if u and v, one of them is a scalar multiple of the other. Right? So the second inequality is equality if and only if u and v are, one of u or v is a scalar multiple of the other. What about the first one? Right, what about the first one? To have the first equality, it's this picture I've drawn on the side here. That equality will only hold if the inner product of u and v is actually a real number. Right? And in fact, it's got to be a non-negative real number because I've taken the absolute value of it. So the first equality holds if and only if the inner product of u and v is a non-negative real number. That's the only way to get the two red lines in that picture to be the same length. Okay, but now note that if u is a scalar multiple of v, then the inner product of u and v is the inner product of u and lambda u. Sorry, I'm actually doing this. I've just written it wrong in the notes. It doesn't matter. I will fix it. Lambda v and v like this, which we know you can pull a scalar out of the second slot. I mean, out of the first slot. In which case, so I want this to be a non-negative real number. It means that I need lambda p to be non-negative. So I already knew that I needed u and v, one of u or v to be a scalar multiple of the other. So if it happens to be the fact that u is a scalar multiple of v, the fact that I need the inner product to be non-negative means that the scalar multiple I took had to be non-negative. Similarly, if v is equal to lambda u, then the inner product of u and v is the inner product of u with lambda u. Now I can pull out to a complex conjugate. I get this. In other words, I need the conjugate of lambda to be a non-negative real number by the same reasoning as before, which means I need lambda to be a non-negative real number. Right, so in order to have equality, I have to have the second one, which means that u or v should be a scalar multiple of the other. But I also need the first one. And if I think about what that means, it means that the scalar multiple I took actually was a non-negative scalar multiple in order to get equality in both steps. Otherwise, one of them would be a strict inequality, in which case you wouldn't get equality. So overall, this shows that we have this triangle inequality with equality if and only if essentially the vectors point in the same direction. Okay, so maybe I should talk about, right? So in other words, if you actually want u plus v to equal u plus v, you need like this to be u and this to be v. This is the only way to get the length of this vector to be the same as the sum of the lengths of the two vectors. That doesn't look like it's going in the same direction. I swear it is. Okay, but again, in this picture, v is pointing even in a positive scalar multiple of u. If you had the situation where you had this was u and this was v, then u plus v would be this vector. Okay, these don't, I know these don't look parallel. Right, this would be u plus v. And in that case, the length of u plus length of v will be bigger. Right, so in order to have equality, you actually need them to be going in this actually the same direction. If you're ever sort of deviating off path or you're going backwards, then it will be strictly shorter to go directly to u plus v than to go first via u and then via v. That's the whole point. Okay. So, maybe you can tell I'm feeling a bit frazzled today. Let's just call it here, huh? Bit of a shorter lecture than normal. It's the end of the section, though. So on Wednesday, we'll start 6b, which is on orthonormal bases. I suspect that will take us, maybe one day, maybe 2 days. Then we'll do 6C. And then, hopefully by the end of this course, we get somewhere in the middle of chapter 7. I think I said in the syllabus that we would cover most of chapters 1 through 7. I think that's a pretty good goal. If we could get to 7B, that'd be great. I think that's very doable. And we'll probably actually get past there. We probably will do all of chapter 7. All right, I'm just rambling. See you on Wednesday.